All right, hi everybody. Here's our lecture for Math 60 for those of you watching online. And we're going to cover section 1.3. I know in the previous video I listed 1.1, 1.2, and 1.3, decided not to do 1.3, so this video is going to cover that. As always, for the folks in the room and on Zoom, stop me, ask questions. Just because I'm recording doesn't mean you can't talk. This is not a video lecture done in front of you. This is a lecture for all of you that I'm recording for other people. All right, so section 1.3 is all about multiplication and division. The first thing I'm going to say is a reminder. Section 1.1 was addition and subtraction, and we talked about how these two are similar operations, right? They're kind of two sides of the same coin. Well, multiplication and division they're also two sides of the same coin. And technically it's only the same amount, but I'm going to say even more because subtraction was pretty easy to work with, even when it's like kind of complicated subtraction. But a lot of times when we're working with complicated division, it makes more sense to write it as multiplication. So multiplication and division even more are two sides of the same coin. We are more often going to write multiplication as a type of, we're more often going to write division as a type of multiplication than we need to do when we work with subtraction. All right, so let's look at multiplication first. And I want to remind you of my four representations of mathematics: symbols, words, numbers, and pictures. And how we can move from one to the other. I really like the picture approach for a review of multiplication and a review of division. Multiplication can be thought of as repeated addition. Let's see, 4 times 3 is 3 sets of 4. Or we could think about it also as 4 sets of 3. So that's the words. When my kid was starting to learn math, and I was, as a math teacher, I was like, you're going to learn math, and he loved it, because he could tell I was excited about it. And we started doing multiplication pretty early. And this is exactly how I talked about it. I didn't actually ever say 3 times 4. The times is just some random word that we came up with. I said, what's 3 sets of 4? 3 and 3 and 3, or 4 and 4 and 4 make 12, right? So 3 sets of 4 I could write as 1 plus 2 plus 3 sets of 4, which is 12. Or I could think of it as 4 sets of 3, 3 plus 3 plus 3 plus 3, which is also 12. But I really like, as I said, thinking about it as pictures. So 4 times 3, well, I'm going to go 1, 2, 3, 1, 2, 3, 4. there's my 4 sets of 3. Sorry, I say this backwards a lot. There are my 3 sets of 4. And in total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in a very real way, multiplication is drawing rectangles. Especially when we work with whole numbers or integers. Get to decimals, it changes a little bit. I could also write this as, in terms of drawing rectangles, 1, 2, 3, 4, 1, 2, 3. All right, and now I have, here's my 4 sets of 3. But all I really did is I rotated the rectangle. I worked a lot when I was younger with my dad, who was a general contractor. And so we did a lot of patios, did a lot of fences. Multiplication super important, right? You have to figure out how much area am I enclosing. Multiplication very often is area, which we usually think of as physical area. What's the area of the desk? What's the area of the room? But it can be area in a more kind of flexible way. Anytime you're multiplying one number by another, you're creating a kind of an area. Okay. Let's do an example of thinking of multiplication as an area. So I'll rewrite it here. A patio is 4 meters long by 3 meters wide. I'm picking those numbers again so we can reinforce the 4 times 3. But I got to do meters because 4 feet's not very big. I'll do a tiny patio. Meters makes more sense. Let me add a word just to be really clear. A rectangular patio. What is the area of the patio? And the units are square meters. So again, I really like the visual or the pictures representation. 1, 2, 3, 4 meters long, 1, 2, 3 meters wide. And then I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the area is 12 square meters. Each of these little squares, it's a square. That's why we call it a square meter, because each of these little grids is a square. And we have 12 of them. And we get 12 of them because we take our 4 sets of 3 or our 3 sets of 4. We call the units square meters because each unit of area is a square. That is 1 meter on each side. Now, in the US, if not in a lot of other places, we don't get a lot of practice thinking about how big 4 meters is, right? But in general, a meter is about 3 feet. So it's a nice sized patio, right? Not giant, but enough for a carne asada. By the way, at the end of this, I'm gonna write down the most common Spanish phrases for addition, subtraction. I don't actually know division, but maybe one of our Spanish speaking students knows the word for division. Then I can learn something too. Yeah. Okay, so there's another reason we call it square meters though. And this is really important because this is going to imply when we're not just multiplying distances, when we're not multiplying lengths by widths. And let me show you. 4 meters by 3 meters. If I think about what I'm doing, I'm multiplying the 4 by the 3. That gives me the 12. But I also multiply in parentheses, or in quotation marks, I also multiply the units. So that becomes meters times meters. And we have a word when we multiply something by itself. We say we square it. 12 meters squared. Or 12, often you'll see just the M for meters. Right? And this is read 12 square meters or 12 meters squared. It's written in either way. So as we get more into multiplication and look at repeated multiplication, if you're not familiar with the notation of the little 2 up above, that's okay. That's one of the things we're going to learn in this class. But I wanted to point out that not only do we call them square meters because they're actually square meters, they're squares, but also because when we multiply units, we end up with meters times meters, which we say is meters squared. Cuadrado, right? Metros cuadrados. Yeah. Okay. All right. So we talked about various properties of addition, and we have similar properties for multiplication. So let me get down into the fuzzy dark area. So these are similar to addition. We have the commutative, order doesn't matter, order of the numbers. Commutative property, order of the numbers doesn't matter. And that we actually looked at 4 times 3 is 12, but also 3 times 4 is 12. We have the associative. This is the order of the actual multiplication. Doesn't matter. So if I do 4 times 3 times 2, I could do the 4 times 3 first, times 2, which is 12 times 2, which is 24. I would like all of you as part of your practice here to be able to easily multiply any 2 one-digit numbers by each other, right? That should be mental math for sure. I would like you to work on multiplying 2-digit numbers by 2-digit numbers, eventually get to all the way up to your 12s. But calculators can help you learn that. That's okay. Anyway, if I change my order of, of the actual multiplication, and I do the 3 times 2 first, that's 4 times 6, which is also 24. Doesn't matter which multiplication I do first. In general, work left to right if there aren't parentheses. Because as soon as we mix different operations, we have to be careful. But if there aren't parentheses, pick the left to right. It'll get you the same answer. Okay. And then we have one more property, but I can't fit it on here. In addition, we had what we called our identity property, where adding 0 to any number doesn't change it. We have the identity property. For multiplication, which is any number times the number 1 is unchanged. So if I take 5 times 1, I still get 5. If I take negative 3.2 times 1, I still get negative 3.2. We're actually just about to get to that squared notation. But before we do that, I need to talk about all the different ways that mathematicians write multiplication and how it can be super confusing. Any questions so far? Okay. Different ways to write multiplication symbols. The nice thing about addition and subtraction, and there's only one for addition, it's a plus sign. Only one for subtraction, it's the minus sign. But there are a bunch for multiplication. There is the dot. That's what I'm generally going to use when I'm working with numbers. 4 times 3 equals 12. The book usually uses the dot when working with numbers also. There is the little x. 4 times 3 equals 12. I'm going to ask you not to use this. And the reason I don't want you to use this is because we use the letter x to represent a variable all the time. And sometimes even it's not a little x, sometimes like it's a big X. So I'll write it here. Also don't use this. You might have to see it sometimes. You might have a textbook that uses it sometimes, but it gets really confusing once we move into algebra where we use x as a variable. The parentheses. 4 times 3. Two terms next to each other with at least one set of parentheses means multiplication. Our book doesn't really use plain parentheses when multiplying numbers, but there are going to be lots of times when you do use plain parentheses to represent multiplication. And we're going to see it more often in something like, I'm going to multiply 4 by the quantity x plus 2. Right? This means 4 times a quantity x plus 2. The dot parentheses. This is mostly used for clarity. So instead of doing 4 times 3, I could do it 4 dot parentheses 3. Just to really drive home we're doing multiplication. And this is super useful when we're multiplying negative numbers. 2 times -7. You might see 2 parentheses -7, and I think that it's a little more obvious I'm doing multiplication when I have the dot there as well, because I see just a minus and I wonder, wait, hold on, is that multiplication or subtraction? Even with the parentheses. And then there's the last one that's used mostly for variables. The word in English is juxtaposition, which is a fun word to say, but it just means next to each other. 2x. It's really only used for variables. Two x is 2 times x, or 2 parentheses x. Or if you really want to confuse someone, 2x, multiplication symbol x, letter x, which I won't even write down. So lots of different ways that we write multiplication. There's no consistency between people, between books, between, like, I don't even have consistency in among myself because sometimes I forget because they all just mean the same thing to me. So I'll try to write like this, but I'm going to forget sometimes and write it like this. And developing that ability to see there are different ways to write it, and these all mean multiplication. That's part of the skill I want you to work on. All right. Questions about our different ways to write multiplication? Cool. So let's talk about exponential notation. The book calls it exponent notation, but whatever. And this is a compact way to write repeated multiplication. We already actually saw that once. The area of a 4-meter by 3-meter patio is 12 meters squared. There's our exponent. I don't actually know where the word exponent came from. A synonym of exponent is power. So raise something to a power, or raise something to the exponent. Now that's on units. Let's look at exponential notation for numbers. If I want to multiply 3 by itself 7 times, I can write that like so, right? 3 times itself 7 times, or 3 multiplied by itself multiplied by itself 7 times. It takes a lot of writing, but it is super clear what's going on. I'm saying 3 times 3 times 3 times 3 times 3 times 3 times 3. There are 7 multiplications. So I'm going to write the number 3 because that's what I'm multiplying by itself. And then up here in the exponent, I'm going to write the 7. Much easier way to write that repeated multiplication. Especially when you start dealing with really big numbers. Like if you're looking at the number of atoms in a grain of sand, you're looking at trillions and trillions and trillions and trillions of atoms. You don't want to have to write a super long number. You can write it using exponential notation. Or on the other side, something teeny tiny, right? Something very, very, very small. You can actually write that using exponential notation as well. So what would be the exponential notation for 4 multiplied by itself 5 times? Give yourself a shot. Write first what's called the expanded, which is this list of multiplications, and then give yourself an equal sign and write it in exponential notation. In expanded notation, we have 4 multiplied by itself 5 times. And if I wanted to write that in exponential, what would the big number down here be?
4.
Yep. And how about the small number up there? 5. Yeah. The big number is called the base. It's the base. The little number is called the exponent or the power. And I can put this in words a lot of different ways. I could say 4 to the 5th power, or 4 to the power 5, or 4. There's not really a word like squared or cubed. There's not a word for 5. 4 raised to the 5. Or raised to the 5th power. So if you see raised, think exponent. Okay. These are big numbers. Let's actually look at what 3 to the 7th is. So I'm going to grab Desmos. And I'll use just the calculator function here. 3 to the 7th is 3 times 3 times 3 times 3, 3 times 3 times 3. Right, all the way up into the 2000s. And my notation, if I want to do it compactly, 3, I can grab this keypad, and the A to the B says no matter what I choose as my base, now I get to put up in my exponent the 7th. And if you want to use just the keyboard, you can do Shift 6, which makes the little caret sign. That's the exponent. So sometimes if you're seeing, oh, you couldn't see that, sorry. If you're seeing math typed by computer, sometimes you see the little caret sign. This means exponent. It's because some math type, like wants to put everything in a straight line instead of moving stuff up and moving stuff down. It uses the caret to indicate that it's moving things up. And that was a number that grew pretty quickly, 2,187. Let's look at 4 to the 5th. For 5th. All right, that grew pretty quickly as well, 1,024. And now a word of caution. We don't have like a commutative property with exponentials. 4 raised to the 5th power is not, in general, equal to 5 raised to the 4th power. There are a couple exceptions to this, but in general, they're not going to be equal. 4 multiplied by itself 5 times is not going to equal 5 multiplied by itself 4 times. We already found out that 4 to the 5th is 1,024, and I can tell you that 5 raised to the 4th is 625. Those numbers are vastly different. So the order that you write the base and the exponent matters when you're doing exponential notation. All right. Questions about exponential notation? Folks on the Zoom call, you can do the raise your hand thing, and I think it'll float somewhere that I can see it. And if I don't see it, you can unmute yourself and say, hey, Peter, I have a question. Okay, division. Division is the opposite operation for multiplication, just like subtraction is the opposite operation for addition. Okay, let's look at 4 times 3 equals 12. This means 4 sets of 3 is 12, which means if I divide 12 into 3 equal sets, there are 4 elements in each set. And B, not an X. These are all equivalent statements. Multiplication and division are really 2 sides of the same coin, because I can say a verbal multiplication for the sets of 3 is 12. It's the exact same information as saying, if I divide 12 into 3 equal sets, there are 4 elements in each set. One of those takes a lot fewer words than the other, but they mean the same thing. Let me show you the picture. Here's 12 squares. And if I divide that 12 into 3 equal sets, there are 3 equal sets. Each set has 4 elements. Okay, so four times 3 equals 12 is the same as 12 divided by 3 equals 4. So this is our division symbol. I'm going to call it the inline division symbol. It's the one we use when we want everything to be on the same horizontal line. It's more often to write the number that we're dividing on top, and then a horizontal line, and then the number of sets on the bottom, and then the result on the end. They have fancy words. They're in your textbook. If you find you have questions either on your worksheet or on your homework that asks you, what's the name of this? What's the name of this? What's the name of this? Look it up on page 27, but I want to stay away from using too many hyper-focused vocabulary words. I want to focus on the operations. If 12 divided by 3 equals 4, then what do I get when I divide 12 by 4? 3, exactly. It's not quite an associative property or a commutative property. It maybe has a specific name. I don't think it does. Nope, doesn't have a specific name. But if I divide 12 into 3 equal sets, there are 4 elements in each set. If I divide 12 into 4 equal sets, there are 3 elements in each set. What happens if I divide 5 into 20 equal sets? And all of a sudden we leave the world of whole numbers, right? Back when mathematicians said, I can divide 12 into 3 sets and I get 4. All right, that's fine. All right, I have 12 basketballs. I split them into 3 groups, 4 basketballs in each group. But what if I tried to divide 5 basketballs into 20 equal sets? I can't do that. But I could do that with a pizza, right? And so now we have fractions. There are 1/4 in each set. And this expands our numbers to include fractions. So we were working with all whole numbers. Then when we started doing subtraction, we said, wait a minute, now I've got negative numbers. Multiplication, that's fine, it's just still whole numbers. But as soon as I allow myself to do division, all of a sudden I have more numbers, the fractions, and the word for this set, the set of all integers and fractions, positive and negative, is called the rational numbers. Rational comes from ratio, which is another way to say fraction. So that's useful information. We're expanding our numbers as we're adding in additional operations. And again, I like the visual. Let's suppose that, well, pizzas are a good way to start because it helps us see that we're working with a whole. 1 whole pizza. If I divide it into 6, which is normally what I do when I do my pizzas, because they're not that big. One whole pizza divided into 6 equal slices. Each slice is 1/6 of the pizza. And we can do that with the rectangle approach as well. The circle approach, the pizza approach, or the pie approach can make it a little more clear that we're dealing with fractions instead of whole numbers, because, right, each of these slices, it's not like it's one of my squares. But I am going to show you how about we do a Chicago style deep dish pizza, right? That's rectangular. So this is still one pizza. And now I'm going to divide it into 3 long slices. Into 3 equal slices. Each slice is 1/3 of the pizza. So it kind of depends when you draw your initial shape, you have to decide how big that initial shape is. This big rectangle here represents the number 1. Before, when I drew that same rectangle, it represented the number 12. Right, so you just kind of have to keep that in mind if you're thinking about it visually. Okay. There are a couple other ways to write division. So let me go back and say how to write division. We have the inline method, 12 divided by 3 equals 4. Order matters definitely here. 12 divided by 3 equals 4, that's true. But 3 divided by 12 is definitely not equal to 4, right? So you do your bigger, or this is, I guess I need the words. The number that you're dividing comes first. The number of sets you divide into comes next. And then the number of elements in each set is what you end up with. The ratio or fraction notation is the other one I showed you, where you do the number you divide on top, the number of sets on bottom, and the number of elements in each set is what you end up with. We can kind of split the difference if we want to do it all in one line. And we do a slash. All right, so that's like the angle division. It's kind of like the ratio method or notation, but it gets it all in a single line. And then there's the, I don't know if there's a word for this. I'm going to make it up. The house notation. You put your number in a house. And then, so the number you divide goes in a house. The number of sets goes outside the house. And the number of elements in each set goes on top of the house, or sometimes comes after the equal sign. This notation is mostly used when you do big divisions by hand, so you can do it step by step. This class, we don't do big divisions by hand. Was it this class where I said I don't do big divisions by hand? I use a calculator? Yeah. So this notation allows you to organize your work when you do big division by hand, sometimes called long division. But that's what we have calculators for. Actually, there's one other notation which is really useful. And this is where I said multiplication and division are really two sides of the same coin. We're going to call this the multiplication notation. So if I do 12 divided by 3, and I don't want to do division at all, I can see that as 1/3 times 12. Dividing by 3 is the same as multiplying by 1/3. Dividing by any number is the same as multiplying by 1 over that number. Dividing by a, when a is any number, is the same as multiplying by 1 over a. And this is a really, really flexible tool that allows us to expand division way beyond the simple divide 12 into 3 sets. Now we can divide complicated things and keep track of all of that much more easily. So this one, the multiplication notation, is the most useful notation in algebra for division. Okay. We're doing good. You're hanging in there. I appreciate that. One more topic in division, and then it'll be time to work on the worksheets. I'll be encouraging you, and Yasi will be encouraging you when you do division questions to practice writing all your divisions using the multiplication notation, just to get used to it. Multiplication and division involving the number 0. 0 is really great with addition and subtraction because it doesn't change anything. 0 tends to cause issues with multiplication and division. 0 times 3 means 0 sets of 3. If I have 0 sets of 3, how much do I have? 0, right? Well, that's nothing. And 0 sets of 3 bananas is 0 bananas. 0 sets of $3 is $0. Hi, Elias.
Hello.
This is our dean here at Woodburn. If you haven't met.
Hello, students. I'd like to time to say hi.
Yeah, let me pause our video because I'm doing some recording for an online class, and that way they don't have to listen to us off screen. All right, 0 times 3 is 0 sets of 3, and that's going to be 0. The 0 times any number is always 0.
Rules for life.
Rules for life. Our second rule is 0 divided by 4. Well, this means split 0 into 4 equal sets. How many elements in each set? Anybody? 0, right? If I have 0 bananas and I divide them into equal sets, they're going to be 0 bananas in each set. 0 divided by 4 is 0. In fact, 0 divided by any number equals 0, except for 0. Can't divide 0 by 0, but that's our next rule. And I'm breezing through this a little bit faster so that we have more time for our worksheets. So far, so good. 0 times any number, yeah, that's 0. Oh, before I move on, let's see that rule 2 is actually the exact same as rule 1, because I can use my multiplication notation. 0 divided by 4, oh, well, that's just 1/4 times 0. And that's rule 1, where a is 1/4. All right, so a lot of our rules in mathematics just kind of fall out from previous rules. That's that idea of building on knowledge little by little, rather than having to say, I'm learning something totally brand new. And our third rule is where we run into problems. Let's divide 2 by 0. This means I could say split 2 into 0 sets. I don't even know what that means. So instead, I'm going to say this means how many times do I have to add 0 to itself to get the number 2? 0 plus 0 plus 0 plus 0 plus 0. Am I ever going to get there? No, right? It can't be done. There is no number of times that I get to add 0 to itself and end up at 2. I can add 0 to itself as often as I want. I can't even get to the number 1. I can't even get to the number 1/2, right? Or the number 1/millionth. 2 divided by 0 is undefined. That's the word we use to say it can't be done. Any number divided by 0 is undefined, including 0 divided by 0, because we say so. Yeah, it makes the math work. The only rule that I've never been able to break in mathematics, by break, I mean expand my worldview, is you cannot divide by 0. That's basically the one rule in all of mathematics that's not broken. A black hole, you all know what a black hole is? Super intense gravitational point, the mass of the sun and the size of a penny, so dense that light cannot escape it. A black hole is what happens when you divide space by 0.
Don't create black holes on your homework or your.
Yeah, fortunately, black holes are very unstable unless they have the mass of the sun or more. So if you were to create what's called a microscopic black hole, it would evaporate almost immediately. Humans have created microscopic black holes already. They've contained them in magnetic fields and they've evaporated. Now, if one ever got out, it might start growing and that would be an issue. But anyway, the point is you cannot divide by 0. That's it. That is the end of this section. I'm going to stop the video. Thanks for watching.